The IEEE Transactions on Haptics has a new podcast format that is designed to help you stay abreast of topics in haptics while you're on the go, by providing a brief summary of the articles in each issue. This podcast gives an overview of the 8 articles found in the July through September special issue on Haptic-Human Robot Interaction. This first article attempts to address the question, can a robot be made to shake hands like a human? Its title is, Towards Perceiving Robots as Humans. 3 handshake models face the Turing-like handshake test, by Abraham et al. This paper presents 3 models for a simulated handshake and evaluates human acceptance of these models versus a real handshake. The 3 models were based on passive physiological dynamics, playback of recorded handshake motions based on identifying leader-follower roles, and a machine learning-based approach. The experiment was conducted by having participants hold the handle of a desktop phantom force feedback device and a power grip, as if they were shaking another person's hand. The goal of the study was to identify what makes a human handshake human-like. The experiment was conducted with 2 naive participants at a time, and each held the handle of a desktop phantom. The 2 phantoms were linked to allow local teleoperation between them. One participant provided human handshakes, while the second participant sometimes experienced the real handshakes of the first participant, corrupted with varying levels of noise, and other times he experienced a simulated model. This participant's job was to answer which of the handshakes was more human-like. The authors found that the played-back leader-follower and machine learning models were perceived more human-like than the passive model. The main audience for this research would likely be motor control and psychophysics researchers because of the paper's focus on understanding human-like movements, but may also be of interest to roboticists interested in building human-like robots. The paper's main contribution is in the presentation of 3 models for human handshake and the assessment of their relative human likeness. This next article presents new approaches to implement and compare methods for providing haptic guidance. Its title is, The Task-Dependent Efficacy of Shared Control Haptic Guidance Paradigms, by Powell and O'Malley. The authors present a hypothesis that the inconsistent results found in prior shared control guidance studies are due to interactions between the specific type of guidance that was provided and the task that was performed. They propose a novel guidance taxonomy to help classify and compare shared control haptic guidance methods, and present a novel haptic rendering algorithm based on a virtual proxy to create more complex guidance methods. The goal of the research is to determine how the choice of task and type of haptic guidance affects training efficacy. The authors utilized 2 training tasks and evaluated 4 shared controlled haptic guidance paradigms. They trained 50 novice participants to perform path following and target hitting tasks. Participants controlled the position of an on-screen pointer using a 2 degree of freedom haptic joystick. The authors found that it is critical to properly match the type of provided guidance to the task dynamic characteristics, and that many times the types of guidance, especially assistive guidance, can actually impair training. The main audience of this study is anyone with an interest in how humans acquire visual-motor skills, but would be of greatest interest to designers of robot-mediated training systems for applications such as pilot training, surgery, or rehabilitation. The main contributions of this research are the author's shared control proxy model for implementing shared control haptic guidance and their guidance taxonomy, which facilitates an easier comparison of their results to prior work. This next article proposes a novel method to guide a person's hand motions by interacting with their opposite hand. Its title is Simultaneous Perception of Forces and Motions Using Bimanual Interactions, by McAmis and Reed. This paper presents a method for providing haptic guidance by providing forces to one hand in order to guide the motions of another hand. The method is based on the ability of humans to easily move their hands through similar paths, such as simultaneously drawing circles with both hands. The goal of the research is to gain a better understanding of bimanual interactions. Participants interacted with a virtual environment holding the stylus of a phantom force feedback device in each hand. The authors first characterized how well an individual can couple the motions between their two hands. The understanding of bimanual motions was then used to test how well an individual can recreate another person's motions using the authors' proposed bimanual training scheme. Participants then used bimanual guidance to identify the orientation of a rod embedded in the soft material. The authors' results show that participants could identify the orientation of a rod equally well when compared to being manually guided through the desired motion. They also show that there is an approximately 50 to 100 millisecond delay between feeling the force or motion applied to one hand and being able to recreate it on the opposite hand. The main audience of this study is anyone who is interested in training physical skills or the understanding of the sensory motor skills of humans. The main contributions of this paper are the new method for training individuals to properly interact with devices and a new method of interaction. It also provides fundamental understanding about bimanual interactions. This article seeks to understand how people utilize redundant degrees of freedom to manipulate a virtual object. Its title is Risk Coordination in a Kinematically Redundant Stabilization Task by Mazia et al. This research utilizes a novel haptic interface that is capable of providing haptic feedback for wrist roll and flexion, and uses this interface for the control of a simulated inverted pendulum. The inverted pendulum is rendered with only a single degree of freedom, and the participants were given both roll and flexion inputs to control the pendulum, hence resulting in a kinematic redundancy for manipulating the virtual pendulum. The goal of the paper is to investigate how kinematic redundancy plays a role in dynamic manipulation of a simulated object. 20 participants were asked to move an inverted pendulum and balance it for a specific amount of time by using two elastic elements. One, a rotational spring at the base of the hinge of the simulated pendulum and controlled by the angle of the forearm, and two, a linear spring attached to the top of the pendulum and controlled by wrist flexion. The task is redundant because there are many ways of coordinating the two wrist motions to balance the single degree of freedom pendulum. The authors found that participants used the roll degree of freedom to stabilize the pendulum when it was linked to stiff springs, and used both degrees of freedom when softer springs coupled their motions to the pendulum. The main audience of this study likely includes roboticists and human-machine interaction researchers, as well as human interface designers. The paper's main contribution is to show that the tuning of elastic elements in a simulated object can be used to force different users to follow the same patterns of muscle coordination with the wrist inputs. In the example of robotic surgery, modulating the haptic feedback could be used to guide surgeons to adopt a coordination strategy and learn specific movements by exploiting the right sequence of muscle activations. This next article explores several haptic device designs and methods for driving these devices for the purpose of guiding human limb motions. Its title is Evaluation of Tactile Feedback Methods for Wrist Rotation Guidance by Stanley and Kuchenbecker. This paper presents 10 forms of tactile feedback for the guidance of wrist rotation using 5 wrist-mountable haptic devices, each of which was controlled to have pulsing or steady motions. The 5 devices were capable of tapping, dragging across, squeezing, twisting, or vibrating against the user's wrist. The goal of the study was to assess which forms of tactile feedback provide the most accurate and responsive form of human limb motion guidance. The devices were evaluated in a series of 3 tasks, which had participants rotate the wrist to turn in the indicated direction, reach and hold a target angle, or follow a continuous trajectory. While wearing each of the haptic devices, participants grasp an instrumented rotary handle to record their wrist motions. The authors found that people move most quickly when the cue's direction is conveyed through the location of the tactile stimulus or steady lateral skin stretch, whereas people responded more slowly to feedback types that rely on a spatial tactile pattern or pulsing cues. The main audience of this research would be those interested in human movement training, including rehabilitation, robotics, and psychophysics researchers. The paper's main contribution is the evaluation of 5 wearable haptic devices and associated control algorithms for achieving fast, accurate limb motions. This next article aims to improve telehaptic interactions through the addition of a compact tactile feedback device. Its title is A High-Performance Tactile Feedback Display and Its Integration in Teleoperation by Sarakoglu et al. This paper presents the design and integration of a compact tactile pin array into a teleoperation system. The system's operation is based on the display of surface shape to an area of the fingertip through a 4x4 array of tactors moving perpendicularly to the skin surface. The tactors are spring-loaded and are actuated remotely by DC motors through a flexible tendon transmission. The system is suitable for applications including virtual reality, minimally invasive surgery, and teleoperation. The goal of this research is to demonstrate the performance benefits from the combined use of tactile plus kinesthetic feedback in a teleoperation task. Performance of the tactile display was evaluated through a teleoperated contour following experiment, with the author's pin array integrated into the handle of an omega-7 force feedback device and used to teleoperate a KUKA robotic manipulator. The experiment was performed under 2 conditions, with force feedback only and with both tactile and force feedback. The author's results show an improvement in teleoperation performance when both tactile and force feedback are presented to participants. The main audience of this study would be those interested in tactile feedback and its integration into VR and teleoperation systems, as well as researchers interested in haptic hardware design and the psychophysics of touch. The main contributions of this paper are to show the integration of a compact, high-performance tactile display integrated with a teleoperation system, and to demonstrate the benefits of this tactile feedback in a teleoperation task. This next article seeks to better anticipate the movements and coordination between human dancers using a novel dancing robot. Its title is Control of a Robot Dancer for Enhancing Haptic-Human Robot Interaction in Waltz by Wang and Kusuga. This paper presents methods for modeling a human dancer and uses a robotic dancing partner to validate the proposed control algorithms. Experiments are conducted using 2 control designs based on state estimates of the human dancer. While prior work of the authors has focused on intention estimation, the focus of this work is on estimating the coupled dynamics of the dance pair and to assess its effect on the robot's ability to follow the lead of a human dancer. The authors used an inverted pendulum model to approximate the human dancer's body dynamics. The robot uses a force sensor and 2 laser scanners to estimate the human dancer's state. To reduce interaction forces with the human dancer, both admittance and inverted pendulum controllers were experimentally evaluated. The authors show significantly better performance when using an inverted pendulum robot controller. This paper will be of greatest interest to human-robot interaction researchers and those interested in modeling the dynamics of walking or walking-assistive devices. The paper's main contribution includes a novel method for inferring a human's motions during human-robot interactions using laser scanners, and a filter-based method for estimating human state. This last article aims to improve interactions between humans and robots through the use of haptic cues. Its title is Supporting Negotiation Behavior with Haptics-Enabled Human-Computer Interfaces by Uz et al. This paper investigates how human-computer interaction can be enriched by employing computers with behavioral patterns that naturally appear in human-human negotiation scenarios. The study utilizes a game that incorporates 2-party negotiation between a human participant and a computer. During this game, the participants are confronted with a computer opponent which can display different behaviors, such as concession, competition, and negotiation. The game uses haptic and audio-visual cues in conveying negotiation-related behaviors. The goal of the study was to identify methods that allow humans to communicate with computers in a more intuitive and natural fashion. The game is structured such that the participant and the computer collect coins and avoid obstacles in a virtual 3-lane road in a scenario that is somewhat analogous to the classic video game Frogger. The two players must cooperate to avoid obstacles and get coins that lie in the middle lane. The author's study found that haptic cues provided a significant benefit to humans in identifying the computer's interaction behaviors. The main audience for this research is human-computer or human-robot interaction researchers, but it will also be of interest to haptics, multimodal, and cognitive interaction researchers. The paper's main contribution is in the development of a model for enabling haptic negotiation between a human and a computer, and showing that participants were more successful in differentiating the computer's 3 programmed negotiation behaviors when they were provided with haptic cues. This concludes our podcast of the special issue on Haptic-Human Robot Interaction for the IEEE Transactions on Haptics. Hope you'll tune in again for our next issue.